We now see how to deal with probabilities, and Julia has a very elegant package to deal with everything related to probabilistic analysis, that is the distribution package. And the idea here is that rather than having for each different distribution different functions, let's go just to create a distribution object and then work with the same functions over this distribution object. So you can see here a table where is given the constructor for the different kind of distribution. For example, for Bernoulli is Bernoulli, and you indicate as argument the probability, or for exponential you give the rate. So here are the discrete distribution, here the continuous distribution. Attention a little bit on the parameters, because the different languages, different packages have different can parameterize the distribution in different way. For example, the normal here, even the normal is not the same. Here in Julia, in the distribution package, is parameterized with the standard deviation. In other languages it may be common to use the variance. So the first things that we do is to create our distribution object with the parameter of interest. Here is a normal with mean 10 and standard deviation 3. And let's start to get some information about this specific distribution. So here we can retrieve the mean, of course, is 10. The variance is the standard deviation raised to square. We can get the median, of course, equal to the mean for the normal. And here we can ask a quantile of the distribution at the given value. So here is the inverse of the cumulative distribution function at value 0.9, and is the value of x at such value, so it's 13.8. And of course, if I get the CDF at this value, I go back the 0.9. Something specific is that for PDF, the function name is PDF, whatever it is, a discrete or continuous distribution. So it doesn't. I think in Python we have PMF and PDF, probability mass function, and probability density functions. Here we just call PDF whatever the distribution is, discrete or continuous. And something very nice is, I find it very elegant. We already saw how to random a number, so the default random at the end is uniform from 0 to 1, but we can sample from whichever of this distribution, but just giving the distribution object as first argument to rand. So here I am sampling 1000 element out of this distribution of this normal 10 free. And here you really see the beauty of multiple dispatch, because this random function will work with all the other arguments. For example, here I just put one number, so a scalar, so I get a vector, 1000 elements, but I can have a multidimensional vector, multidimensional array, and here I don't need, when you need to make a new distribution, you need to define very few methods specific to how to sample from your distribution. All the other higher level interface doesn't need to be touched, because it will automatically, as much as the low level function works, you define the low level function, the high level function as well will work with your new object, even if the guy that programmed this higher level function didn't know nothing about your specific distribution. So here we can sample, we can plot our data. This density function is a recipe of the stats plots. So here I should have, here is how is plotted. And as I said, the stats plots allow to plot a function, probability function. So here I'm plotting the theoretical function, and you see here that with 1000 samples we're pretty close to the theoretical density that we would have. Another tools that the distribution package provide is a simple fit method based on maximum likelihood estimator, where given my empirical distributions and a family of distribution, I can retrieve the parameters. Of course, there are a lot of statistical packages to do this in a much more precise way, and providing information on how good is this fit. But this is a very simple way if you want to have a quick fit of some data. If instead of fitting some data to a probability distribution, you want more in general to fit a curve, a function, you can use SQFit, that is very flexible as it allows you to fit any arbitrary function, whatever linear or non-linear, using simple last squares. And let's use it to fit a logistic growth curve, also called as Verholst model. I hope my pronounce is correct, but I do not guarantee. So we use the package, we add some, and we have some data here. The data are related to the, as I am in forestry, in data from Scott Spine volumes of a stand. So here I have the age from 20 years every 5 years to 90 years, and here I have the volume of the stand at the different years between 20 and 90. And we can plot it to see that indeed the growth resemble a logistic functions. I was going to create our model. So our logistic model will take age as input, and then we'll have a set of parameters, and this is the parameter, this is the equation of the logistic functions, where we have the first parameters, and then we have the exponential of the second and the third parameter. For some reasons, SQFit want a vectorized form of the function. So here he want a vector of input, all the different ages, the vector of the parameters, and will output the vector of y of the volumes at the given ages. And to obtain a vectorized function, we just simply add a dot, very nice in Julia, to broadcast our scalar function. We give some initial parameters, as this in general is a non-linear optimization. We'll see later optimization, but behind here there is an optimizations. We need to provide some reasonable parameters, and in case of the logistic model, the three parameter used, the first represent the maximal growth that the logistic function will reach. So we put one, looking at the data, we put 1000. We put some growth rate, but here I put 2%, and the age at which more or less we reach the median volumes. So here I put 50. They don't need to be precise at all, but just reasonable with the background that you have of your data. So I have set these initial parameters. At this point, I can fit my curve. So I use the function curve fit. I put the model again in a vectorized form. I give the vector of input, I give the vector of output, and the vector of the initial parameters. When this function terminate, I will have the fit object, and within the fit object I can extract the parameters. So here is a vector where the fitted parameters 692, 7% and 45 years. I can also get the residual here. However, this residual for each observed volumes can also be computed manually. How? Well, by calling our model with our observed data, our fitted parameters, and removing from our model the observed volumes, and the result should be the same. It is the same? Yeah. So I can check it here. Okay, so together with the residual, I have other information about the fitting, that is the standard error of the estimations for each parameter, and the confidence interval. Here I can specify at 5% significance level. So here is the standard errors, and here for each parameter I have a tuple of the confidence interval. So let's gonna plot it. Here I just set my x. I give a little bit more years in order to plot also a little bit more here. I first plot my fitted volumes. I obtain my fitted volumes by apply my model with the fitted parameters over the x, and here is the logistic curve that I fitted. I can print my observed volumes as a scatter type. So here are the volumes really observed at the given ages, and here are the residuals. So pretty nice fitting.